Good morning to all. Welcome to the course of Analog Communication. Today we are going to discuss about amplitude modulation. So, content of today's presentation is modulation and mathematical analysis of the amplitude modulation technique. So, after completion of this lecture, the students can able to do the time and frequency domain analysis of amplitude modulation. So, communication mainly focuses on sharing of information. So whenever we want to share the information between two persons, if the two persons are very far apart, then with the help of some techniques and devices, the information can be transmitted. So for that, the main important and basic technique is nothing but modulation technique. So this modulation technique is mainly consists of two things, that is the baseband or message or modulating signal, and it is used for performing the efficient transmission. And the other name for the modulation technique is frequency translation. So the process modulation can be explained with this block diagram. So here we have a device called modulator. So for that we need two inputs. One is a message signal and another one is the carrier signal. When these two inputs are given to the circuit called modulator, it will produce the output, that is nothing but the modulated signal. So generally this requires message signal and carrier signal to perform this process. Generally this message signal is a low frequency signal and this carrier signal will be a high frequency signal. So before discuss about the modulation in depth, first we will see what is the need for the modulation. So generally the modulation techniques are used for wireless transmission. So in the wireless transmission, antenna plays a vital role. So whenever we are going to design an antenna, the antenna length should be considered. So here the antenna length is mainly depends on the wavelength of the signal. So whenever we are going to design an antenna, the antenna should have the length of So the antenna length is mainly depends on the quarter wavelength. So here, so whenever the frequency of the signal is very low, then the antenna length will be increased because frequency and the wavelength both are inversely proportional. So whenever the frequency will be high, then the wavelength will be reduced so that we can design the antennas with smaller length. So that is the main advantage why we are going for modulation. So whenever we want to transmit more number of signals on a common communication medium, then these signals may get mixed up. To avoid the mixing of signals, with the help of the modulation techniques, every signal can be transmitted with a different carrier signals, so that by using the common medium, we can transmit all the signals at a time. So these are all the two important reasons why we are going for the modulation techniques. So the definition for modulation is changing the characteristics of the carrier signal with respect to the message signal. So a signal generally will have three basic characteristics. They are frequency, phase and amplitude. If the amplitude of the carrier signal will change in accordance with the message signal, then the modulator will produce a signal called amplitude modulated signal. So similarly, whenever with respect to the message signal, if the frequency and phase of the carrier signal will be changed, then according to that a frequency and phase modulated signals will be produced. So from the definition we can write the mathematical expression for the amplitude modulation. So here we will consider the message signal as x of t and the carrier signal as c of t. So then the modulated output can be represented mathematically as s of t. So here the message modulated signal s of t can be written as in the form of a plus x of t into cos omega ct. So this expression is designed based on the definition of the amplitude modulation. That is, the carrier signal, the amplitude of the carrier signal is changes in accordance with the message signal. So the carrier signal c of t can be written as AC cos omega ct. So according to amplitude modulation definition, so in order to perform the modulation process, here the message signal x of t varies the amplitude of the carrier signal. So after performing the modulation, the modulated signal can be represented as a plus x of t into cos omega ct. So this expression is basically from the definition of the amplitude modulation. So now if I'll bring this, amplitude outside, then this can be written as the modulated signal can be represented as 1 plus x of t divided by a into cos omega ct. So here this x of t divided by a can be called as m, where m is called as modulation index or modulation factor. Otherwise it can be called as degree of modulation, depth of modulation or amplitude sensitivity. So these are all the different names we can give for the term m. So here m can be calculated as modulus of x of t, that is the maximum amplitude of x of t, which is divided by the carrier signal amplitude. So based on this m, the amplitude modulation can be defined into three types, that is over modulation, under modulation and critical modulation. So whenever the m value is less than 1, then amplitude modulation is called as under modulation. So here if we will consider in this graph, here the x of t is our modulating signal, it is an arbitrary signal. Then we are considering the carrier signal is nothing but a cos omega ct, which is having the amplitude a and the frequency is nothing but omega c. Whenever these two signals are given to a amplitude modulator, and if we will consider the condition as m is less than 1, that means the modulus of x of t divided by a is less than 1. If this ratio is less than 1, then that condition is called as under modulation. So for the under modulation, the graphical representation will be like this. So here if you observe, the envelope of this modulated signal will be similar to the message signal x of t, and the inside the amplitude variations are nothing but from the carrier signal. So whenever this fraction, that is the ratio between the modulus x of t and divided by a is equal to 1, then we can observe this is the output of the amplitude modulator. So here you can observe that this is the reference point. So whenever the ratio is greater than 1, that means your modulation index is greater than 1, then that amplitude modulated signal is called as over modulated signal. So here the envelope of your message signal is mixed up. Due to the mixing up, here the carrier signal is having some phase reversal. So out of all these conditions, the preferable amplitude modulation depends on the m value less than 1. So why it is preferable? Because at the receiver side, whenever we want to perform the demodulation, so the demodulation process extracts the message signal from the modulated signal. So whenever your m is less than 1, then only the extraction process will be carried out in a proper way so that the message signal can be extracted. So now we will discuss about the frequency domain analysis of this amplitude modulated signal. So in order to see the signal in the frequency domain, we need some tool, because generally the signals whatever are available in the real world, they are time domain signals. In order to analyze them in frequency domain, with the help of transformation techniques, we can perform that. So here, in order to see this amplitude modulated waveform in frequency domain, we will use Fourier transform. So for this modulation process, we need two inputs. The first one is the message signal x of t, and the next is the carrier signal c of t, and then the modulated signal is s of t. So now we are going to apply Fourier transform for all these three signals. So first, after applying Fourier transform, then this x of t, Fourier transform of x of t is known as x of omega. So because here we are considering a signal which is an arbitrary in nature, so we are not going to give any kind of mathematical representation in its frequency domain representation. So now we will consider the carrier signal and we will apply the Fourier transform to this carrier signal. So here the carrier signal is nothing but A cos omega ct. So if we'll apply the Fourier transform to this, then the Fourier transform of A cos omega ct is nothing but A pi delta of omega minus omega c plus delta of omega plus omega c, because this cosine transform will produce us two impulses if we will apply the Fourier transform. So now we are going to find the Fourier transform of the modulated signal s of t. So the Fourier transform of modulated signal s of t can be represented by s of omega, and this can be found by using Fourier transform of s of t, where our s of t is given as, in the previous slide we have seen, A plus x of t into cos omega ct. So in a simplified form, this can be written as f Fourier transform of A cos omega ct plus Fourier transform of x of t into cos omega ct. So already we know what is the Fourier transform of A cos omega ct. So from the carrier signal we can write it as A pi into del of omega minus omega c plus del of omega plus omega c. So now we have to apply the Fourier transform for the second term. So here if we will apply the Fourier transform for this x of t into cos omega ct, this can be written as 1 by 2 x of omega minus omega c plus x of omega plus omega c. So now we will draw all these three frequency domain representations of this message signal x of omega and the carrier signal c of omega and the modulated signal s of omega in order to see the frequency spectrum. So the frequency spectrum can be drawn by taking the magnitude value in y-axis and the frequency values in x-axis. So because we have considered the message signal is an arbitrary signal, is an arbitrary signal. So, in an arbitrary way, we can draw its frequency domain representation, and we will consider this message signal will have the frequency from 0 to plus omega m and 0 to minus omega m. So similarly, the carrier signal can be drawn. So here the carrier signal, whatever we have considered is a cosine signal. So it resolves two impulses. So one is at plus omega c and another one is at minus omega c with the amplitude of a pi. So now, we will draw the frequency spectrum of this modulated signal. So here we have two impulses. With the two impulses, we have the message signal spectrum. But this message signal spectrum, if you will observe, here it is shifted to minus omega c as well as it is shifted to plus omega c. So that means it introduces some delay and in advance in the frequency domain. So now, so this shifted versions now we can draw. So first we'll draw the carrier signal. One is at plus omega c and another one is at minus omega c with the amplitudes of a pi. And then with respect to this plus omega c and minus omega c, our message signal spectrum is shifted. So this 0 is shifted to plus omega c in order to produce x of omega minus omega c. So here the lower frequency is minus omega m. So I can write it as omega c minus omega m. And similarly here this is plus omega m. Whenever we are adding, we will get omega c plus omega m. So similarly on the other hand, we can write this is the spectrum of x of omega plus omega c. So here we will get minus omega c minus omega m and minus omega c plus omega m. So mainly this frequency spectrum is used for finding the bandwidth of the signal. So here the bandwidth can be found by using the highest frequency component and the lowest frequency component. So according to this amplitude modulation, the highest frequency component is nothing but omega c plus omega m, and the lowest frequency component is omega c minus omega m. So if we will subtract these two, we can observe that the bandwidth of amplitude modulation is 2 omega m. So mainly the frequency domain analysis is used for finding the bandwidth. So here in this derivation, we have considered some arbitrary signal to find the frequency domain representation of amplitude modulation. So now we will consider a single tone signal, and then we will see its time domain and frequency domain representation. So first we will consider x of t as a single tone. Why it is called a single tone? Because it is having only one frequency. So we will consider the message signal is nothing but am cos omega mt, and the carrier signal c of t, as usual we will consider it as a into cos omega ct. So now we know the modulated signal output, that is s of t, can be written as a plus x of t into cos omega ct. So now we will substitute x of t in this expression. So that is a plus am cos omega mt into cos omega ct. Now, if I'll do some simplification on this expression, so this can be written as a cos omega ct plus am cos omega mt into cos omega ct. So now, so here it is in the form of cos A cos B. Suppose if I'll substitute cos A cos B formula in this, then it is equal to 1 by 2 cos A plus B plus cos A minus B. So if I'll substitute that one, then I'll get A cos omega ct plus am by 2 cos of A plus B, that is omega c plus omega m, plus cos A minus B omega c minus omega m. So in this representation, we can give names for each and every term. That is, the first term is known as the carrier signal c of t, and the frequency term omega c plus omega m, it is known as upper sideband. And similarly, for this omega c minus omega m, this frequency term is called as lower sideband. So, from this single tone modulation, we can say that after performing the modulation, the signal S of t, the modulated signal S of t consists of three terms. The first one is C of t, and the second one is upper sideband, and the third one is lower sideband. So now, if I'll apply the Fourier transform in order to see its frequency domain representation, then I'll get two impulses in the frequency of omega c, and similarly for two impulses I will get omega c plus omega m and omega c minus omega m. So if I'll draw all these things, then, so this is my message signal with the amplitude of am pi, with the frequency of minus omega m and plus omega m. So this is the single tone signal frequency domain representation. And similarly, the carrier signal already we have seen. So with the amplitude of A pi, minus omega c plus omega c, and this is the starting point, its origin. And then this modulated signal, so in the discussion we have seen, first the carrier signal will be there, okay, with the amplitude of A pi at minus omega c and plus omega c, and then this signals will have two side bands. One is at omega c plus omega m and another is at omega c minus omega m. So with the amplitude of am pi by 2. So this is called lower sideband and this is called upper sideband. So similarly, we have the replicas in the negative region. So minus omega c minus omega m and minus omega c plus omega m, the amplitudes of AM by 2. So this is about the frequency domain representation of single tone signal, single tone amplitude modulated signal. So now in next class we will continue about power content in amplitude modulation. Thank you.